learning, but also computer vision, audio, and some other methods, but mostly machine learning. So everything which is here is actually the network and the backpropagation and the TC is taken from Accord. Now, when it comes to learning, this is something which I wrote. So reinforcement learning with the Q-learning is my implementation of Q-learning, which I got from, I don't know, some Python example, which then I translated to .NET, simplified it a bit, made it some more complex in some other bits. Then supervised, this is actually, those components can be used to get, in a very hard way, but you can get the neural network from TensorFlow, which is another framework, and use it in Grasshopper. You cannot train it in Grasshopper, but you can use it. And unsupervised is k-means clustering, and Markov chain is something different, but anyway, k-means clustering mostly. So I wrote my own k-means clustering algorithm, which is very simple, but it's there. So before we can start learning, teaching anything, the code, we will, I mean, today we have, I think we have like 1 hour left till 2 p.m. and then we have a break till 4 p.m. as far as I remember. So we'll just spend this hour on getting through those components. And then afternoon, we'll just do some machine learning actually with them, right? So there is quite a lot of components and we need to understand why do we need those components, first of all. So the problem in Grasshopper is that when you, let me show you, I will show you the problem in Grasshopper. The real problem is, not sure if it's slow enough, but yeah. So you see that outputting 100,000 zeros from a component takes 0.3 seconds, right? If we take 1 million items, it takes 3.4 seconds, then 10 times more, which means that just outputting those 1 million zeros will take 3 seconds. So it's very inconvenient in Grasshopper to work with big data sets, okay? And so there are other machine learning plugins, like I think Lunchbox has some machine learning tools, but they are working with data trees. So it's kind of limited in a way that it cannot handle big data. I mean, it can, but it'll be very slow and inconvenient. So I created OWL with that in mind, right? So passing that to another component like that, we can do something like that. You can see that there is this freeze in the interface, but we can even do like a equal x plus y. That will also take some time. And it's not the addition which takes that much time. Addition takes almost no time in this case. It's actually 8 seconds. 8 seconds is for getting that integer, figuring out what is the type of that number. So there are different types in programming, right? There's integer, floating point, double precision, single precision, complex numbers, text, and so on. So Grasshopper needs that time to figure out what do you actually input in the X. And then when it outputs it, it also will figure that out. So this is why it takes so much time here. This is why it takes so much time here. This type conversion is called casting, right? So casting from one type to another will take time. Grasshopper does a lot of casting. And that's because it tries to be user-friendly. That's why you don't have to care about whether an integer is a double or not. Is it a floating precision or not? You just put it into the component, and it will figure out how to use that, right? If you have an integer input, and you put in a floating point number, like 0.5, it will round it up or down, depending, right? So Grasshopper does it for you, but the cost of it is those really long time. It takes a really long time. So sometimes it takes more time to cast, like here. The actual computation, I mean, we can just show you. Maybe it's not a good idea. Anyway, it's not a good idea to show. I mean, it's just too much time wasted. But anyway, we can have this computation. I will tell you it takes, I mean, we can do it differently. So 1 million times addition, right? This will be a bit faster to demonstrate. I think it's print. So is the, so here I will just run this code just to illustrate that I'm running like 1 million times this addition, 10 times 20, and the stopwatch will tell me how much this 1 million additions took, right? 1 millisecond, right? So it takes no time. 8 seconds is only for casting those inputs and outputs. 1 millisecond is to add those numbers together, right? It's no time. It can even probably say 0 if you recompute it. Yeah, it's 1 millisecond, more or less nothing, right? So addition is not a problem. In fact, there is a hardware on the CPU which adds numbers together. So whenever you have an algorithm which runs on hardware, it's actually hardware implemented, it's super fast. Okay, so that's why we need those custom types to handle, let's say, 1 million numbers times multiple cases, right? So you can have an image 1000 by 1000 pixels, grayscale, that's 1 million parameters, and you want to have a big number of those images. You can do that with OWL. Learning will be slow. Learning is based on CPU, not GPU, so it's a bit slow. But in theory, you can do that. So we have, how do we start the numbers, right? So let's say that I have an image. Okay, maybe I will do the image first. So I will show you how to make those later if we have. Just So you see that this image is 0, 1, 2, 0, 1, 2, and then 3, 3, 3. So this shows you those numbers are transferred into the image. Now, yeah, don't worry about that. But here, this image can have, as I said, can have 1 million values, and then you can display it that way, right? Yeah, if you have questions, just ask. So we have, yeah, so basically we have a tensor, right? And then if I have multiple tensors, so I can have another one, which will be something like that, right? So if I connect it here, this is another tensor. I cannot display two of them at once, right? I can only display one of them here in this component, but anyway, we can have two tensors. And then, so each tensor is a case, right? As I told you before, in supervised learning, we want to teach the network about different cases. So we may talk about the frog again, those values may be describing some particular case of a frog, right? And there are 9 measurements of different parameters of a frog. Now, in any good study, there will be hundreds, if not thousands, of frogs collected and measured. So we need to have a way to put those 2 frogs together. So that's why we need a tensor set. Now, again, we could have a list of tensors. Like, notice that it's a list of numbers, right? So a tensor is a list of numbers, essentially, and then a data set will be a list of tensors, so a list of numbers. But this list of tensors of observations, right? So again, maybe measurements of a frog population, it can have like 1 million cases as well. Probably not, but anyway, it can have millions of cases. Again, Grasshopper will be very slow in getting the data around in the interface. It will be super slow. So we want to couple those tensors together, and we'll do that by using tensor set. So tensor set is nothing else than a list of lists of numbers, right? So when we create, maybe I can show you the full names, right? This will be a bit easier. So we have construct tensor set, and then in the output, I have just 1 tensor set with 2 tensors, right? So usually you would want to have some way of reading the data from a file. So there are different ways of reading that data, and just putting it in the code here and running it and using it for training, right? Yeah, so those are the basic things to know, that there is tensors and tensor sets, list of numbers and list of numbers. Each tensor is a particular case, and then each tensor set is just a whole data set. Again, a frog with 10 parameters, another frog with 10 parameters, 2 frogs. So some study, right, of frog population. So tensors, tensor sets. Now, yeah, so why tensor? Tensor is, if we Google tensor, what is a tensor actually? Why? Okay, that's English. Nope, not this one. English. Yeah. As we say, a tensor may be represented as a potentially multi-dimensional array. Why do we need multi-dimensional arrays? Because we don't really need, I mean, in some cases we need that, in some cases it's not really important, but classical machine learning, we don't need arrays, we just need a list of numbers. But with things like convolutional neural networks, you work with images. So it's important to be able to represent stuff as image, just like here, right? So we have a tensor, which is a list of numbers. I have to reshape it to a 3x3 tensor, right? So you can see that this is a list of numbers, but then when I reshape it, it's a tensor 3x3, and then I can display it as a bitmap. Convolutional neural networks work with images, so it's just most natural to, I mean, technically you could code it so that it still works with a list of numbers, but it's just more convenient to work with images. So tensor essentially is a multi-dimensional array, as you saw by the definition. Multi-dimensional means that it can have, you can pack the numbers in a list, you can pack the numbers in an array like an Excel spreadsheet, but it can also be a volume, right? So you can have different numbers in X, Y, and Z directions. Then you can have even 4 dimensions, or 5, or 100 dimensions, doesn't matter. Tensor is essentially the most abstract way of naming a multi-dimensional array. So I took the tensor as a name and the idea from tensor set. So tensor set is this framework for machine learning made by a think it was developed by Google at some point, and then yeah, it's not really TensorFlow. I'm sorry. So TensorFlow is this Google Brain team, but TensorFlow essentially uses tensors to pack the data, and it's just the most convenient way to use use the data basically. So Tensor is from that. Tensor set is something which I had to add on top of that to be able to work with a lot of tensors in Grasshopper, right? So you won't find tensor sets anywhere else, I think, but tensors are quite popular in other frameworks. Now, again, multidimensional tensors can be images, can be volumes. Reshape is something which you'll find in a tensor set as well. So you want to reshape it depending on different cases. Reshaping is not really removing any data from the tensor, it's just rearranging the array, right? So we could have, let's say with 12, right? If we have 1, 2, 3 again. With 12, we could have 3 by 4 or 2 by 6, right? Or 6 by 2. And you can see it doesn't remove any data, it just rearranges the array, right? So this is just reshaping. We'll not use that, but it's just good to know that, because if you were to use TensorFlow, it's used quite commonly there. And convolutional neural networks will use that as well. So what we can do else with tensor, we have reshaping, we can have addition. So addition is basically two tensors. I can add the same tensor. What it will do, it will simply, okay, maybe we can remove that. So it will simply have 2, 2, 2, right? So we have a 3D tensor. I mean, 3 values in a tensor. It's a one-dimensional tensor. It's a vector, basically. One-dimensional array is essentially one vector, right? So tensor, and you see that 2, 2, 2, it adds those values together. So there's the addition, subtraction, similar. This we'll discuss later. Highest activation will, so let's say that I have values like 10, 100, and 3, right? So highest activation will sort those values. I mean, it will pick the first 3 values from a tensor which are highest. So if I have another one like that, it will only display the number of dimensions I will input, right? So it will give me the top 3 highest values. So they're indices. Number 1, that's 100, and the actual values. So, oh yeah, I did the addition here. So again, here. So 100, 10, and 3, right? So this is highest activation. This will be used for classification. So whenever you have a neural network, we'll just discuss them a bit later. You look for the highest activation, which will tell you what is the case in classification. Tensor crop is just cropping images. So when you have 2D, it's cropping this. Tensor split, it's very rarely used, actually. I never really use it. I think I used it only when I used TensorFlow. So TensorFlow takes, okay, so if you're using TensorFlow and you're using tensors, when you have, let's say, a list of 10 tensors, each tensor has 3 values, but it's just 1D. Like, so it's just like, that. Like it's 5 or 3 values in a tensor, and then we have 10 tensors. In TensorFlow, when you want to couple those tensors together as a data set, you will actually have another tensor which will have 1 more dimension, and it will pack them in an array, right? So like a spreadsheet, we'll take each copy of that tensor or each tensor, and it will just append them, adding 1 more dimension. So that's where the tensor split is important, because we can have, let me show you what I can do with that. So again, 2 by 5, let's say. I'll just put more image, put more values here. Shape is 2 by 5, right? So this tensor has 10 values. Then I reshape it, so it's 2 by 5. It's an array to the array, and then when I split it, it splits it back to 2 tensors. So this is how it works in TensorFlow, right? So it splits it back into 2 tensors, which are basically this list and this list, right? So reshaping merges that into 2 by 5, splitting does the opposite more or less. Or actually removes the last dimension because you can have a 3D shape and it will just remove the first. If it's 2 by 5 by, let's say, 10, it will remove the 2 and split it into those 2 5 by 10 tensors. So this is just a split. Threshold, I can't remember what's that. I really rarely use that. I think it just crops the level here. So if it's, I think it will be that, right? So 0, 1. Okay, let's see. I can't remember what this component does. I think it has a bug actually. 0. Yeah, I can't remember what that is. Somehow manipulates the numbers so that there are no peaks, but I can't tell you why it's doing that. I can't remember exactly. Yeah, this just shows that this component is never used. I never used it in any workshop, but it should technically trim the values. And tensor statistics will just tell you what is the number of values and the shape. So 2 by 5 if you want to extract this shape, right? So this is it. Then we have, so this is tensor, right? So this is how we can manipulate a list of numbers. Now tensor set is a bit more specific here. So we have, let's say, let's leave this guy just like that. Let's make it a bit more realistic. So 0.5. Yep, some tensor. Let's have 2 of those guys. And maybe let's change this one as well. Okay. So now let's construct the tensor set. So primitive, construct tensor set. Let's put those 2 guys together. And now we have a tensor set to work with. Now with tensor set, we can do add noise. We'll discuss it later. It's actually very useful. So adding noise will, yeah, maybe let's display it, or maybe let's deconstruct the tensor set to data tree. So we can convert the data tree to tensor set. So each branch becomes a tensor. They all become a tensor set. Or you can have a tensor set and convert it into a data tree. So the opposite. It's quite simple here, right? So you can see that I get those 2 lists back here when I deconstruct the tensor set into a data tree. So I want to do that just so that I can show you how the noise adds to this, right? So the noise will add some small value to the numbers, right? And then the seed is just randomness seed. If you ever use a random component, you will know what it does, right? And then constrain is whether to constrain those numbers to a particular domain. So by default, it's 0 to 1. So this is this one. And yeah, so adding noise is quite useful, actually. Yeah, tensor set average. So it will just average the values. So it takes the first one. Oh, I'm sorry, it just does that right away. So you can see that the first one is the average of the first from the first one, and the second from the second one, and the first from the second one tensor. 0.15. Nothing special here. Sometimes useful. Bounds tensor set, that will tell you what are the boundaries. So what are the numbers which are in the data set. So 0.1 to 1, that's the biggest one. Dimension, so sometimes when you have, let's say our frog example, right? We collect the measurements from different frogs, the length, let's say, and the width, or actually the weight and the width or length of the frog. So we would like to know what is the span of all the lengths, and we'll use that, but we don't want to measure all the values from all of the properties. We just want to have one property. So that's why you would change the dimension, right? So let's say that this is width. So you want to have the first dimension only, right? To set the boundaries. Now the smallest and the largest example. This is quite useful as well. So this is bounds. Interpolate, that just, going through the tensor set. So I think it just takes this guy. And this should, I mean, it's just a linear interpolation, but I'm not sure why there is only 2 tensors in the output here. Anyway, not really useful. I mean, I never really used it. Merge tensor set is useful on the other hand. You can have multiple tensor sets and you can just merge them. So instead of 2, you'll have 4 tensors. What is different in OWL than it's different in TensorFlow is that in TensorFlow, you cannot mix different tensors, differently shaped tensors. So you cannot have a tensor set. I mean, the tensor, which is, let's say, 2 by 4, and then another one which is 2 by 10. You cannot put them into one collection. In OWL, you can do that, and it will, just merge it like that, because it's just a list. It's not an array in any way, right? So it's a list. Pick tensor. So picking tensor is something like list item, but you don't have to deconstruct the tensor set to pick the tensor. It will just, get one from the entire tensor set. Merge, remap. Remap is essentially remapping the values. So we have the source 0 to 1, then let's take this component. Yeah, so the source is 0 to 1, target is 0 to 1, and you can see nothing really happens, but if you would like to increase the range, then you can just put another target here, so 0 to 2, and the values are multiplied by 2, just like remap numbers in Grasshopper. So shuffle tensor set, useful as well. So whenever you have a huge collection of tensors, you want to shuffle them while you're training it, right? So sometimes the neural network, when it learns, it just learns faster if you feed it with the data in different order. That is how it works. And it prevents from overfitting as well. So we'll talk about that when we discuss neural networks. So this, so it's basically shuffling, like jitter in Grasshopper, shuffling the list. Split tensor set, again, this will, yeah, this is also useful, but I cannot really demonstrate it here. Maybe I can use duplicate data. Let me delete all of that. So I'll duplicate it by 50, right? So I will have 50 tensors. They're all the same, but doesn't matter. I construct the tensor set, right? So I have 50 tensors, but I want to split it. And the proportions are the proportions I would like to split it. It splits, I think it's random, or not really random, I can say right now. It's not random. It's split, but anyway, you can see that it tries to match the proportions. So we have 50 tensors, those proportions. This will create 2 tensor sets and split them into with those proportions. Now the thing is that This is really useful when you do actual machine learning, because usually when you train a neural network, you don't test it against the same data, right? When you train a neural network, you test the accuracy of the neural network by using different data sets, right? So let's say that you have 100 images. You would always want to train with 80 of them, but test and evaluate how good it is with 20. We'll discuss it later as well. So this is why we have the split tensor set. Now we have subsample. I think this is just randomly picking a number of tensors. Again, it was meant to do that, but not really useful. I mean, tensor set stats, that's again just statistics. So count is how many tensors we have. Homogeneity, I think it's, I'm not sure if it's not the typo, but homogeneity, it tells you if all the tensors are shaped the same, right? So as we discussed, we can mix those shapes in tensor sets. There can be different tensors, differently shaped tensors, and this will tell you if all of them have the same shape or not. And trim tensor set, it will just trim the values. So whatever the values are, we can say that whatever is whatever is above or below will get trimmed, just like that. Right, so right, we can have 0 to 0.5 as well. Everything about 0.5, like 1, will get trimmed. Oh, wait, there is, okay, this one, right? So everything above 0.5 will get trimmed. Sometimes useful, right? So this is sometimes useful. So this is this guy. Now, so those are the basics. Let's get to actually display the tensors. Now, I consider how useful when you want to learn machine learning and you want to do some small-scale machine learning, or you want to find the right training parameters for some neural network. I mean, if you were to do like, 10-hour training, I would rather switch to TensorFlow. I would consider all good for like 2-hour training time. It's not super efficient, right? Efficient is TensorFlow. This is meant to be simple, accessible, and useful with like up to a few hundred, few thousand cases, and let's say 2 or 3 hours training. It's again, it would be perfect if you could do everything, but it's not optimized to do that. It's optimized to be easy to use. And also, display is then very useful, and this gives you a lot of insight into how neural networks work. This is something which you don't really have elsewhere, right? Maybe you have it on websites like this still, but you cannot really. Yeah. So there is this website, Distill, which visualizes different. Oh, it's actually updated. It wasn't updated for a long time. So this still shows you different learning tools and how they work. But I wanted to. Yeah, this one. So you see that this is just a very simple, usually a very simple example of how things work. And visualization tells you much more than just looking at the parameters, right? It's actually optimization of the neural network. They are trying to make an argument why momentum really matters. So we'll discuss that later. But the thing is that visualization is the key to understand why something works or not, in my case, at least. So display will be very critical in observing how your network performs, and there's always a question: when should you stop training, or when do you know when it's working? It's not easy to figure it out, because training, as I said, it can take hours, but if you don't plot the training process in any way, so for instance, the error rate of the neural network, it might work or it might not work, but you will never know if it's fully trained or not. You have to somehow display this information, right? So those tools will be very useful for that. We'll actually set up neural network training in a loop, and then we'll use those components to visualize it. And we'll observe what they do. And by visual feedback, we'll really well understand what is going on. And we'll just discuss that later on, I think today afternoon. So let's see what we can do. We can do tensor 2D preview, so we already did that. It figures like it's only one tensor at a time, but it shows you the tensor. If we have like 6 values, we can do like reshape and visualize it as a 2D bitmap, right? So 2 by 3. So this is the 2D. Yeah, sometimes useful. So sometimes it's good to see if we have the right data. If we read the data from a file, then it's good to visualize it and just confirm that it's properly read. I cannot really show you this one yet, but this basically displays in Rhino viewport the labels. Tensor set cloud. Maybe let's do the tensor set display. So tensor set display is the most common. Like we always use tensor set display to visualize the tensor set. So we have, let's not duplicate the data. Let's have just those tensors, right? So we have construct tensors. We have 2 tensors. And if I connect the tensor set here, I can visualize those values. Now the warning is that it's not heterogeneous, right? So different lengths. I need to remove one value here, and now it's the same, right? So 5 values in each tensor. By default, the range is 0 to 1. We'll stick to that. So everything in machine learning, you will always normalize. You'll always want to have a 0 to 1 domain, just so that you don't have any bias on the size of the values. You can highlight a tensor. So let's say you can highlight number 0 or 1. I mean, with 2 tensors, it's not really that useful, but you usually have like hundreds of tensors, so you might want to highlight a particular one. If you specify a directory, whenever you refresh this bitmap, it will be saved to the directory with the current date and time. So when you have a loop, you can actually save those files to the loop and make an animation. Let me see if I can find some animation done like that. All the image-based, most of the image-based components in OWL will have that option. Just specify directory, it will do the rest. I just try to see if I have anything which works like that. Unfortunately, not here. Maybe. Second. Yeah, I want to find some nice video. Nope, that's not it. Anyway, I cannot find really the video which I'm looking for, but anyway, when you have the directory, it saves it as an image without the grid. The grid is just for displaying Grasshopper, but it's just a PNG with transparent background and those curves. So you can stack the images with After Effects, or not really After Effects, but you can stack the images with Premiere Pro or any other software, and it will make an animation. And those animations are surprisingly informative. Like, we will discuss the neural networks later on. I will show you like how to read this feedback from here to understand what is going on. It's crucial. Like, it's very, very important to understand what is going on, and it tells you if something is working or not. So we have the the tensor set display. Now we have let's see, the tensor set polylines. So this is another way of displaying the data set, and this is actually useful when you have k-means clustering. This will map the values. So we have 5 values. So each triplet of values will be mapped into a point, and then this tensor will become a polyline. So you can have 9 values, it will become 3 points, and then the polyline will have 2 segments. In this case, we have 5 values. The sixth value, so the z for the second point, is assumed to be 0. That's why they are on the xy plane. The first 3 values are here. The second 3 values are here, and there is an arrow in here, but in the new Grasshopper display, it's not really visible. It was visible in the old Grasshopper, but not now. And the arrow should be just a bit bigger to indicate which triplet comes where. When you have high dimensional data, so a lot of values in a tensor, and you cluster, this preview will really show you the clusters right away. So if you want to know if your data set is meaningful, I mean, if it's meaningful to have any kind of clustering, like, you remember the example which I showed you in the presentation, there was a circle made out of 10 points, but there was no really clear distinction between any groups. Clustering was not really necessary there because there was no clusters, right? There's no actual groups of points in this data set, so it was wrong. But anyway, we can talk about it. In the real world, you will have some groups, right? So when you have this circle with those 10 points around, you will have some skew somewhere, and a bunch of points, like 3 points, maybe will be more on the left, 7 points will be more on the right. But again, this is just 2D. When we have more dimensions, like 10 dimensions, you stop being like, you cannot really perceive that well as with 2 dimensions. So you want some tool, k-means clustering, for instance, to show you the distinction between the groups. And to know if it makes sense to even consider clustering, it's good to have some visualization of the data set up front. So when you have those points plotted in 2D, that's great, because you can see right away if there are some groups or not. But with high dimensional data, it's really hard. But this tool, this polyline display, is actually, it's really useful, and it's really nice to see that. Those different polylines, and it shows you right away that there might be some similar items or not. And this works with, even 100 dimensions, right? So we can have like random, something like that, right? That's just 100-dimensional tensor visualized as a polyline, right? Another one is, let's change the seed, right? You see they are nothing alike. I mean, they are not really alike. But if we take this one and just add a small fraction of noise, so I'm just making noise by hand. So let me add that here on point, let's say, right? I'm adding it here, constructing another tensor, just like that, and adding it here. Now you can see that even with 100, let's put another seed here, even with 100 dimensions, you can kind of see that there are 2 polylines which are similar, right? So this is a really great tool when you want to visualize things. With 2D preview is also possible to visualize it with 2D preview, of course. 1 second. Tensor set display, this one. It's also possible, but again, with a lot of samples, it's not that clear that they are similar, right? They overlap. With 3D, you have like a better overview of that, and you can see that there is some alignment between them. So this is a really nice visualization tool. Just to, like before you even do anything, you can visualize the data set quickly, see what it looks like, and then decide whether it's useful or not to do something. So polylines. Cloud. Cloud is exactly the same. I mean, sort of the same, but instead of a polyline, it will display a cloud, but it will only use up to 6 dimensions. So it doesn't make sense to use 100 dimensions like here, but if we have 6 dimensions, it will visualize the first 3 dimensions as the XYZ, and the second triplet as color. So we have 3 points here. Right? I'm not sure if it's visible, but we have the points, and they are differently colored. That's based on the 6 first dimensions. If you have more dimensions, they just get not really red by any means. And you can toggle between display, so they are just being displayed. If you have 1 million points, you don't want to output them again because it slows down the interface and everything in Grasshopper. You want to display them, but you have to switch the output geometry if you want to get the actual geometry, right? So now you have the geometry, and it's here, right? And the colors as well. But by default, it's disabled because we assume you have a lot of those. So this is the display. Now we have preview classes, not really doable right now. We need some more complex case, maybe later. Feature tensor set, yeah. So from those components, I would like to show you a couple of components from different tabs here. So feature tensor set will tell you, it's an easy way to construct the tensor set. So instead of creating tensors separately and then stacking them together, feature tensor set takes a list of numbers and consider them a feature of multiple tensors. So what do I mean by that? Let's take a series of numbers like that. And this means that in the tensor set, there is 10 tensors with one feature, like one feature, one number. So as you can see, there is 10 tensors. And if I de-tensor set or convert the tensor set to data tree like that, it will create a data tree with 10 tensors, one value per each. Right? I can have 2 features. I just add more features, and that will take 2 features. Right? So just to show you more here, the first one will be 123, and so on. This is also useful when you have a tensor. So we can have duplicate data. I'll duplicate them 10 times because you have to, like, those inputs have to be aligned, right? So they have to have the same number of values, whatever the value is, but it can be a number, it can be a tensor as well, just like I'll do now, right? And you can see that those 10 tensors, so I duplicated the same tensor 10 times. The first tensor gets grouped with the first number from F1 and the first number from F2, and they are here, right? So just stacking the data up. You can also input a point. So again, we need to populate, let's say 3D with 10 points and population here. So the triplet here in the end is actually XYZ coordinates of those points, right? So this is a quick way of getting those values. If you get the line, I think a line is not really that fast to do, so let's not waste time on that. But from line, it will extract 2 points, I think. From a rectangle, it will extract X and Y. From, yeah, I think there are a couple of more ways it can, a couple of more geometries that it can work with. Just try it out. But tensors, numbers, points, lines, vectors, this will be handled by this one, and it can be stacked as different features. Quite useful. I mean, usually I actually construct tensors that way rather than that manual way around, like here. Display IO. Yeah, so maybe we can talk a bit more about loading and saving files. Now, load bitmap will just load a bitmap and create a tensor set out of it, and a tensor out of it. And then we have 3 different ways of saving tensors. So save IDX tensor set. IDX is a file format which is used by a couple of libraries out there, datasets, I'm sorry. So MNIST, that's a one, I'll just show you an image here. So MNIST is a database of handwritten digits, and it's like a benchmark database. It's not too large, but also not too small. Like everything is nicely labeled and organized. And each image is 28 by 28 pixels. That's 784 pixels. I just remember it. I cannot multiply that fast. 784 or 86 dimensions, so pixels for each image. And they are all stored in IDX file. So it's a binary file, and you can read that data set with load bitmap, right? So you can import IDX, load bitmap, load tensor set, I'm sorry, load tensor set, and it will give you a tensor set actually, right, from this IDX file. You can save it as well. So saving will be useful when you want to create some data set. Okay, so let's say you have an example and I know some algorithm which uses neural network to train it with TensorFlow, right? And this TensorFlow algorithm will use IDX as input. So you can create that input file in Grasshopper. So it's much easier, believe me, that it's easier to create it with Grasshopper, if you know Grasshopper, of course, and then run it only in TensorFlow than to do everything in TensorFlow by hand, right? So quickly create IDX files in Grasshopper if you want to use them elsewhere. And almost every framework out there for machine learning will know how to read IDX. The problem with IDX is, again, that each tensor has to have the same size. That is not a constraint for tbin. So tbin means tensor binary. It's just a custom-made format binary for OWL. It will not be read elsewhere. I think we have a Python example on GitHub, how to read that in Python. So you still may actually want to transfer it to TensorFlow. You can read it with Python, but it's not trivial. And then save tensor set to a text file that will create sort of a CSV file. It's not fully CSV, so like CSV comma separated values, it's just a text file with numbers separated by commas, and then each tensor is a new line in that file. But the first couple of digits, numbers in each line will tell you the number of dimensions and then each dimension. So if you have 2 by 3 tensor, I think it will tell you that the first number is 2. So then there are 2 dimensions, and then 2 and 3 are the dimensions, and then the rest will be just the numbers. So it's just a text file, basically. Different ways of handling that. I'm telling you that because if some of you want to work with machine learning in the future with anything like Keras, TensorFlow, or OWL, or anything else, it's good to know how to get the data around, right? So in this paper, which I showed you, where we trained the neural network with 3D scans of the panels, we exchanged the data between Grasshopper and TensorFlow. We used TensorFlow just to train the network, but then the network was, once it was trained, we wanted to visualize the outputs, we wanted to prepare the data up front. We did all of that in Grasshopper because, you know, with one parametric definition in Grasshopper, we can always just, let's say, quickly reiterate and refine the data set up front, right? So as you know, we can shuffle the data set, split it differently in different proportions and so on, just try out different parameters very quickly with Grasshopper. So that's why it might be useful. Not really here. So yeah, I think this is most of the stuff which we wanted to cover in this part. In the second part, so afternoon at 4 p.m., we will be finally teaching the neural network how to do that. Maybe we have like 15 minutes left till 2 p.m. I will just start with just a small intro of neural networks, maybe. So we will be using neural networks today and tomorrow, and then we have another day scheduled in the future where you will have some time to discuss your projects, but let's discuss neural networks. We'll do much more. I mean, yeah, I'll try to do it as quickly as possible so that we have more time today to play with neural networks. But neural networks basically are constructed of neurons. And maybe we can start with an example of a neuron. Yeah. That's not what I wanted. That's a perceptron. This is a simple, old school way of is this good or bad? Not really great. Let's start with a neuron. So a simple neuron. This is fine. No, this is not fine. That's actually a wrong label here. It's not how it works. Nope. Yeah, this is fine. So we take this one. Yeah, there's a lot of research on that because you can, you know how we have face recognizing neural networks? We can actually fool them with painting something on your face and they figure out how to do that. So that's a research on that as well. So this is a single neuron. A neural network is a composition of a lot of neurons, usually stacked in layers. And all the neurons, let's say you have two layers, 10 and 10 neurons in each. Each layer from each neuron from each layer will be connected to all the neurons in the other layer, right? If you have multiple layers, so we talk about deep learning, there's more than a couple of hidden layers. Hidden, we'll discuss hidden later, but you have a bunch of layers, like layers in Photoshop more or less. But only the consecutive layers are connected to each other, right? So we call it a fully connected, the thing which we are going to do is a fully connected backpropagation trained neural network, right? It tells you quite a lot of what we are doing. So fully connected means the layers are fully interconnected. Backpropagation is the way we train it. Before we go there, let's discuss the neuron. So each layer is composed of multiple neurons. A neuron does a very simple thing. So it looks a bit chaotic, but a neuron takes values from the input. So this is a bias. Don't worry about that value. This is what we worry about. So a neuron will take a bunch of inputs, values basically, multiply them by the weight. So the weight of the connection, and then sum this value together, right? So let's say that this is 0.1, like all of the values are 0.1, but there are different weights. So 0.5, 1, and 2, right? 0.1 will become 0.05, 0.1 times 1 is 0.1, and 0.1 times 2 is 0.2. We take all of those values and sum them together. So this is the first step in the neuron. It takes those inputs, multiplies them by the connection weights, and sum it together. When it does that, and then has this activation function. So there are multiple different ways of applying activation. There are different functions which we can use for activation function, but the most popular, or like the classical one, is the sigmoid function, right? So sigmoid function will take that input. So whatever we sum here together, right, from all those inputs times weights, we'll put that on the x-axis. And the activation function will transform that input. So let's say it's free, right? We sum it together, it's free. we read out what is the value from the sigmoid function for number 3 in the x direction. It's something close to 1, right? So 0.95, let's say. So, I'm sorry. So this is what the sigmoid function does, right? So it takes those values, sums them together, evaluates the function, and then gives it the output. So this is the output. 0.95 is the output. So this is what the neuron does. Now, in a layer, you can have multiple neurons, just like that, right? And this is all they do. Like there is nothing more in that. Like all the neurons are basically doing that, summing together the inputs times weights and passing it through that activation function and then outputting it to the next layer. And you can see that each neuron in this layer is connected, in each layer is connected to all the neurons in the previous layer. So it takes all of those inputs, sums them together, applies the activation function, passes that value forward. So yeah, forward is the keyword because the values are passed forward. So they go from input layer. We have 4 values here in the input layer in this image. It means that our tensor, so when we have a tensor set, we actually apply this tensor with tensors, singular tensors. So a singular tensor will have 4 values in this case. And whatever we want to predict or whatever we want to classify about those four values, we'll have 3 classes or 3 values which we want to predict. Depends on what you are doing, classification or regression. If you have, let's say you have 4 values and you want to classify into 3 classes, let's say tall building, long building, and big building or small building, 3 classes. You have 4 dimensions for the building, which might be width, depth, height, and maybe, I don't know, some other parameter. And then the neural network will simply input those 4 values and output the values, which will indicate what is the type of a building, right? High, low, small, and so on. So yeah, so this is it. So when we talk tensors, we think about input layer, and those values will get propagated forward to the output layer, and they at each step, each neuron will do what we just discussed. So sum, activation function, output, sum, activation, output, and so forth. So what training means, what learning means in this case is changing those weights, right? So, you know, the output will be only affected by the weights of the connections, right? This is the only way you can change the output. So of course, if you have 4 parameters, you want to classify this particular building as a high building. So let's say you want to have the highest value in the first output neuron, right? This will indicate that this is a high building, let's say. So you train it, you affect that output only by changing the weights of the connections, nothing else. Maybe we can have it, not really here, that's a bit intimidating. Let's say this one. No. I'm looking for a good representation, like good drawing, just describing it. Not really. Anyway, maybe we can look for back propagation. So back propagation is an algorithm to affect those values, right? Maybe you can see it here. Don't worry about the values, or don't worry about the equations. They don't really mean much here. You don't need to understand them. The thing to understand is that for the input, we input the tensors which we have in the data set, and the output, we also, in the supervised learning, we also need to have the output. So we need to tell in those tensors, in those examples, what do we expect the neural network to output, right? So let's say we have, in this case, we have 2 classes of buildings. Let's say tall and short, right? We have 3 inputs, width, height, and depth of a building, and 2 outputs, which will tell us if it's a short or a tall building. And we need, first of all, we need to have a tensor set for the inputs and the outputs. So we need to show the network what are the expected values for each particular input. The more data you have, the better. You train the network by doing backpropagation. So what it means is that you do that action which we just described with forward propagation. So each neuron sums the inputs, passes them by activation function, and passes it forward. So you do the forward, and you initialize the weights with random values. So in the beginning, the neural network will just pass those values by the random weights, multiply them by random weights, and output some garbage. But this garbage, you compare the output of this garbage with the output which you expect, right? So you tell the network that for this input, you expect this particular output. With the randomized initial weights, you get some garbage. So you compare this garbage to the output which you want to get. You have an error, right? So this error will tell you that the output was supposed to be 1.0, but because of our random weights, the output is 0.2. So the error is 0.8, right? So backpropagation, what it does, it basically reverses the action of the network and passes that error backwards, right? By passing that error backwards, we know how to correct each weight, right? So we know that if the value is too small, we need to increase the weights. If the value is too high, we need to decrease the weights. Now, all the details of that are quite complex. Not getting there, if you really want to know that, I think it's Matt. Just a second. I need to look for this guy, Mateuzs, this guy. So this is, I mean, if you really want to understand, this is the best explanation out there, like exactly how those weights are multiplied, added together, and so on. But there is one image which I want to show you here, right? So this is again the context of a single neuron, where I have an error. I want to reverse the action of that neuron, and this will tell me how do I affect the input weights. Right? If I want the neuron to output a higher value, I will increase the weights. Easy as that, right? But this gets complex with deep networks, right? So when we have multiple layers, the mathematics becomes just a bit more complex because the W1 affects not only the error one, it also affects the error two. So we need to then figure out which value to increase by how much or decrease by how much, depending on the error indicated by that weight. It doesn't really matter. The thing is that you do the forward propagation. It tells you that something, it gives you some output. You compare it with expected output. You calculate the error. You backpropagate the error. Okay. I think that this should be understandable, that this is how it works. That's why we need always, in the training of a network, we always need input and output data. This is not, again, if we revert back to reinforcement learning is trial and error. Do whatever you want, and I will tell you if we're doing it right or not. In neural networks, it's training by example. So I show you what you should input and what you should output. And I have to, the person who trains the network has to show both, right? So just as we had the dishwashing example, I was showing both the input and the output. I was showing like what I expect, right? What is the order of the actions which I have to perform? Again, this is the same here. I expect inputs and the outputs. And I show the network both. And it figures out, the backpropagation figures out how to affect the weights so that the output is what I want. This is a really good, there is no better explanation than that. I would not even be close in describing it to you better than this guy. And he actually walks you through all of the steps, all of the values. You can track the values, which value goes where, and so on. There is something like bias. So bias what gives bias in here is that it's just an additional value to each layer. As you see, it's one value for each layer. It also changes, and you also optimize the network. So you also train the network by changing the bias. But the bias is just giving the network a bit more room to wiggle, basically. So it gives us like one more degree of freedom in how it can change, right? I saw a good explanation of that. If you have a good explanation of that is, let's say you can represent your network as a line, right? So this is your network and this is your data set. 2 points, right? Or maybe 3 points. Okay. So, or maybe 4, or maybe let's give it some meaningful, right? So let's say that this one is orange and those are the blue ones, right? So, or maybe this one will be orange as well, whatever. So if you have this is an abstract, just a very abstract way of thinking about the neural network. The neural network here is represented as the line, which divides the data set into 2 parts. If you don't have a bias, it basically means that you can rotate this line, but only rotate it around the center point of the coordinate system. If you have a bias, you can also move it left and right. So you can also place it like that, right? So this is just this one more degree of freedom for the neural network to move. So this is where the bias comes in. So this is, yeah, it just makes it a bit better in predicting or in training. Bias is like, the only thing which you have to worry about is just weights for now. Bias is just, yeah, like a background thing. Okay, so we have 2 p.m. I think this is a good, if you have some questions regarding those neural networks, we can address them at 4 p.m. For now, it's like, I consider it like a good enough explanation. We could go into a lot of details, but we'll do it during the exercises. So we'll just make a small exercise with the XOR function. I think you got it on the Google Drive, I think, or OneDrive. And then we'll discuss how all of that affects this example, right? So we'll exactly see like what happens when I change stuff, what happens when I change the backpropagation hyperparameters, right? We'll all see that, and then we'll apply it to actually, we'll see, maybe we'll do the classification. But tomorrow we'll want to do autoencoders. Autoencoders use neural networks as well. That's why we want to have those both, because they use the same tool, but in a very different way. Autoencoders will give us dimensionality reduction, so there's interpolation, nice map of subspace, right? But they use the same, everything is the same, we just treat it a bit differently, and it does something completely different. Okay, so I think that maybe we can address the questions after 4 p.m. Okay?
Yes, sure. Okay. So then see you at 4.
Yes, 4, yeah. I will just continue as long as it takes us. I mean, I hope it will be till, like, as we discussed, it was like 6:37. Yes. I can't remember. But
6:30.
We will
but
do
let's
it.
See.
We'll do as long as we have to finish today's schedule. But I think we're right on time, so it's fine.
Cool. Sounds really nice.
Okay.
So thank you for now.
Yeah. See you.
See you.